Okay, sorry for this disruption. Let's continue. So what we are saying is that stress is force by area. In this case, our force is equal to the total pressure, okay, or the force which is resisted by both the walls. So what we do is we write PDL, which is this one, times 2 times thickness L, and 2 times thickness L because there are 2 walls resisting the pressure. Okay, there are 2 walls. So each wall is resisting P, and force F is the summation of both the P's. So that's our equation. This equation is a very well-known equation, and you will come across it if you are doing structural mechanics, if you are doing theory of shells. So this sort of equation will always pop up. Okay, so it's an important equation to remember. Now, this was for the longitudinal stresses. Okay, longitudinal means that the stress is resisted by the walls along the length. Okay, that means longitudinal. Now, as I told you that in the case of pressure vessels, if we have a cap in the end, okay, if you put a stop in the end, okay, what will happen is that you will have on the wall also pressure exerted. Okay, so if you have this wall closed, okay, there are blinds which stops the flow, then that blind will be subject to horizontal force or the same pressure but in horizontal direction. This can be a partition also. Okay, the example is a partition. You can partition a water tank into 2, so you can have forces in this direction develop. Now, as I told you that in the case of longitudinal stresses, and this is stress longitudinal, this is also called stress tangential. That's another important thing. This is stress T. We call it stress T also, which is stress tangential. And this, why is it called tangential? Because it is along the tangent of the length. So normally they call it stress tangential. Now, stress tangential is a function of longitudinal stress. Okay, and the example, as I told you, that if the water is flowing in a vessel, so the vessel will try to open up. Okay, and why? So in order to make this as a vessel, you have to put a joint over here. This has to be seen. There would be a seam over here, and you will have to weld it. Okay, it will be welded. So that either welded or either bolted, riveted, whatever you want to do. But the important thing is that the force which is resisted by the wall must be taken by those items which are restraining it from opening up. Okay, so whatever you have provided, whatever connecting material you have provided, it should be strong enough to stop it from opening up. So this is, as the name suggests, this is called joint. Okay, this is longitudinal joint. In the case of this sort of thing, what happens is, where will you have, as I said, the longitudinal, the stress L's, which are the longitudinal stresses developing. And that is, as I told you, if you either put a blind or if you join 2 pipes. Okay, imagine I've got 2 pipes which are joined together. Now, if the water is flowing or any fluid is flowing, this joint will be subject to tension load. Okay, you might have seen that people also join pipes. Okay, when they are providing water supply to to any residence, they always join the pipes, and that is the joint. The joint is the weakest link. Okay, so this joint should be strong enough to sustain the flow of water. And how do we find out now the pressure? So if there is a pressure over there, okay, there is a pressure on the whole cross section, that will be resisted again by the wall, but this time the cross section. Okay, and that cross section is P11, which we call is equal to pi dt. 2 pi r is the circumference, so pi dt times the longitudinal stress. So what we are saying is that this circle, if we open it up, so this will become 2 pi r or pi d and times thickness. So that is actually the area. Please remember that you can use this equation pi dt only in the case of thin wall structure. This formula is not applicable for a thick wall structure. Okay, so that is an important thing to know. In reality, this would be pi dt plus pi d plus 2t. Okay, but we have just taken pi d and this would be pi d plus t, isn't it? If you take average of this area, okay, this is d plus t. So if I take d plus t, this should be pi d plus t times t. Okay, so area should be pi d plus t times t. That is for the area of the longitudinal stress. Now, because we are dealing with thin wall, okay, so if we open the bracket, pi dt plus t square, this we assume is very small, so we get only pi dt. Okay, do you understand the logic? Why do we omit this t square, pi d plus t, and why not? Because d is the internal diameter. We are just taking internal diameter. So the reason is that it's thin wall, so therefore the thickness is very small. Now, pi dt times the longitudinal stress is equal to, again, pi d square by 4 times pressure. And please notice, this is again, we have taken pi d square by 4. So this can be a spherical stop. But even in the case of a sphere, if the stop or the end plate is spherical, or if it's a straight circular, whatever it is, you will get pi d square by 4 times 3. And the argument is tied to whatever we said in this case. Okay? Force is equal to the projection of the cross section. Okay? Times the pressure. Force is equal to projection of the cross section times pressure. So what I'm saying is that the end stop can be spherical or it can be a straight, it can be a circular plate. Okay? That doesn't matter. You just multiply pressure with pi d square by 4. And so this is pi d square by 4 times p. And your longitudinal, the stress longitudinal is, this d will cancel out with this one. Pi will cancel out with pi. this, then this, P, and this is P, which is a pressure. Okay, this is pressure, internal pressure. Or you can call it Pi, which means internal pressure. This can be also called as Pi, which is internal pressure. So the longitudinal stress comes out to be PID by 4T. So this tells us that the tangential stress is more critical than the longitudinal. If you design a vessel based on your tangential stress, then it will be valid for longitudinal also. Another thing in literature, this joint, which is taking the load stress L, that is called girth joint. Okay, so that's just aside, a tangential talk. Okay, so now what sort of question can you get in thin wall pressure vessels? So at the most, I mean, we can have a scenario that someone might ask you, how much pressure, how many screws should I put or at the longitudinal joint in order to sustain the fluid pressure which is running in the vessel. Okay, so in other words, you have got a straight plate, you make a vessel out of it. Okay, and this vessel, as I said, should be tied. Okay, so how would you find out the longitudinal? How would you find out the attachments over here? How many attachments do you need? And the answer is, like for example, if this is a paper and I want to put, I want to staple. Okay, so how many staples would be enough for this one in order to allow the fluid pressure inside? Okay, how many staples would be enough? That's what I'm asking. Okay, so how would you find that? Again, you come to this equation, stress tangential. Okay, the inside pressure you know already. Okay, you will be given diameter of this vessel, you will be given 2 times T. That is some that's again geometry and it will be given. So you can find out your stress tangential. Okay, now this stress tangential, from this stress tangential you can work out the load P, can't you? The stress tangential times thickness into L will give you the load. Okay, isn't it? So what I'm saying is that imagine I've got this paper and there is some gas or some fluid running through it. I ask you, how many staples should I put on it in such a way that this vessel, this paper, is able to transfer the gas from point A to point B? Okay, that is my question. So what are you going to do? You will come to this equation. Now you know that that equation is not critical. Why? Because that is giving you less stress. So you will go for the maximum stress. Maximum stress is by tangential. Okay? So you will take this stress, multiply that with the thickness of this paper times the length. Okay? Times the length. So that is actually your pressure over here. Okay, so it is this joint. Because this is joined in one location. Okay, this was initially one solid plate and you joined it like this. Okay, so you don't have two joints. You have got just one joint. You can have two joints if I've got this as, if I put another paper on top of it and staple it by two rows of staples. Do you understand my point? In this case, in my case, it's just one row of staples, okay, which I need. So stress T you have worked out. You multiply that with the thickness times length. You get the force. So you find how much force is there, okay? That force which is opening it up. Now that force, if you know the force resisted by one staple, okay? By one staple, if you know that it gives you X kilonewton of X Newton of load. One staple can take 0.01 Newton of load, for example, okay, or 0.1 Newton of load. So if you know it for one staple, you can find out that how many staples are required to resist this load P. Do you understand my point? So that is one way. If instead of staple, this is a steel plate, okay, and there are screws over there, okay, in the case of screws, the screw will be in shear, isn't it? Because if I put a screw over here, it will be under shear stress, okay. So if you know the shear stress resisted by one screw, you can find out based on this P how many screws you can have. Okay, and similarly, if you have weld over here, so if you know the per unit length weld, how much force that weld can resist, it's similar to like a staple. Okay, if you know per unit length this much force can be resisted by a weld, then you can easily work out your number, the size of the weld. Okay, how much thick the weld should be, how much long the weld should be, in order to make it, in order to sustain that life. You understand my point? So that is it. That is your thin wall pressure vessel. Do you have any question? Any question? Okay. So that's it. Thank you very much.